Welcome to Advanced Java Programming at Portland State University. In this screencast, we're going to learn about Java's facilities for doing I/O. These classes and interfaces live in the Java I/O package and provide a myriad of facilities for doing I/O operations. We're going to look at a number of classes in this screencast. First, we're going to look at the Java I/O file class that represents a file. You'll see what we'll be able to do with that. We'll also look at classes for doing byte-based I/O, which are called streams, and classes that are used for text-based I/O, which are called readers and writers. So, Java I/O file represents a file and can be created from a string that specifies its location, or from another file that represents the directory that it resides in, and then the name of the file. And so you get this object that represents a file, and it has a number of instance methods on it that can tell you things about that file, like whether or not it can be written to. You can delete a file. You can ask whether or not the file exists, and then you can get information about its name, if it's a directory, the size of the file, and you can also perform operations like creating a directory that the file represents, or getting its parent file. All of this, of course, is described in the Java docs for the Java I/O file, and so we can find those by looking for the Java I/O package, and the file class. There are also a couple of interesting static methods, a couple of interesting static fields on the Java I/O class. So there are a pair of static fields called separator and separator character, which represents the string or character that separates portions of a file specification. So for instance, this is / on Unix. And there's also a path separator and path separator character, which is the separator for, directories in a path. Colon on Unix. The interesting thing about these two static fields is that they're platform dependent, right? So if I run a Java program on Unix, I ask for the value of the separator character, it will print out a /. But if I run it on Windows, it's \. But because there is this static field, this separator char static field, your program can abstract out that platform dependence. So for instance, let's say that it's reading the name of a file and it's stored in a database. So you go query the database and you get back the string that is the name of the file. And then if you want to figure out what the parts of it were, your code, if it uses separator character, it can run on either Windows or Unix regardless. It doesn't care, and we'll see a little bit, I guess maybe in the next screencast, about how this works underneath the covers. But it's important to note here that they've abstracted out something that's platform dependent into these static fields. There are two interfaces in the Java I/O package called file filter and file name filter that are used for filtering out files in a directory. And this is a really interesting example of object-oriented programming and how an interface can be used to abstract out some behavior and provide a nice clean contract between a standard API like the Java file class and your code and the logic that needs to be implemented by your program. The way that it does it is that each of these interfaces have a method called accept that takes a couple parameters, some criteria, and returns a boolean saying whether or not a given file matches is accepted by that filter, matches some criteria, has some property that's of interest to the filter. There are two methods on the file class, list and list files, that take the file filter and file name filter respectively. And what the list method does is that it returns the names of all the files that are accepted by the file name filter. And so the file name filter object is then consulted by the list method to determine which files in that directory are of interest to that filter or apply to that filter. Similarly, list files will return all of the files that are accepted by a file filter. Okay, let's see an example of this, then we'll come back and discuss why it's interesting and why it's a good object-oriented pattern. So here I have a class called directory filter, and its purpose in life is to determine whether or not a file is a directory. So note here that in our class we must import the Java I/O package, and that gives us classes like file filter and file. And the implementation of this directory filter class is really quite simple, right? Because it implements file filter, it must provide an accept method that takes a file and returns a boolean. And it says, okay, well, if the file is a directory, then return true, otherwise return false. And that's all it does. I also have a class called Java FileNameFilter that implements the FileNameFilter interface, and its accept method takes a directory in which a file resides, the name of the file. And the logic here is really quite straightforward. It says, well, if FileNameFilter ends with .java, then return true, otherwise return false. And so what these two classes do is implement not a piece of data, right? You know, in CS 101 we learned that all objects represent data. They have state, and you can work with that state. Well, these objects, as you can see, there are no fields to these classes. Instead of implementing a piece of data, or providing a piece of data, they provide an algorithm. So basically, by implementing the accept method, these objects provide algorithms. And notice that there's really no need to create more than one instance of these classes because there's no state. Every directory filter has exactly the same behavior. Every Java file name filter has exactly the same behavior. Anyway, and this is kind of what makes this interface interesting, because this interface provides a contract between the Java I/O file class and your program. And we'll see that now. Okay, here is a kind of maybe a little hard to read program main class that finds all of the Java files recursively starting from a directory. So let's start here in the main method. So what does the main method do? Well, it creates a file object from the first command line argument, and says, okay, well, if that file is a directory, I'm going to do something. If it's not, I'm going to print out an error. So it takes a directory. And what does it do with that directory? Well, it creates a new directory filter object. It creates a new Java file name filter object and calls this and assigns them both to these static fields, dir filter and Java filter. Then it calls this find Java files method and given that file to start with. And what does find Java files do? Well, it starts in a directory and it recursively finds all of the Java files underneath that directory. So the first thing it does is that it's going to look at all of the subdirectories it's got to find all of the subdirectories first. And the way it does that is by it's going to find all the Java files in that directory, then look at subdirectories. The way it finds all of the Java files is that it applies the Java filter to all of the files in the current directory. So in that directory that it was given. And so it calls directory.listFiles to find all of those Java files. So here again, what listFile does is it just takes a file filter and calls the accept method on every file within that directory, within its directory. That will return you the list of Java files, and so it'll go through that list and print each one of them out. Now it's going to recurse into subdirectories to find all of the subdirectories within that directory. It calls list files again, and this time gives it the directory filter that's going to return an array of subdirectories. Because remember, there might be in any given directory, there's a combination of regular files and directories, and so these filters will tell you which ones are which. It returns an array of files which are the subdirectories, and then simply iterates over all of them and calls find Java files recursively on each subdirectory. And so when you run it, this is the kind of output you get. You see, first it prints out all of the Java files in a directory, and then will subclass into it will recurse into subdirectories and find all the Java files there. So why is this interesting? Well, again, instances of directory filter and Java name filter do not have any state. There's no fields here. This object encapsulates behavior. It implements an algorithm. That's what it provides. That's its meaning, and that's why you have it. It also demonstrates a nice separation of responsibilities between the interface and the implementation of the interface and the Java IO file class. So all file needs to know is how to apply the filter. It doesn't know what the criteria that's used to filter, and more importantly, it doesn't care. Right? Think about it. Right? Java IO file is a class that's provided as part of the standard JDK, and there was somebody else, probably many years ago now, who wrote that. And so the file object is responsible for understanding, down at the lowest levels of the operating system, how do I go find the files in a directory? But it doesn't know how your particular program is going to want to filter those files. So I suppose it could have just exposed a method which is, hey, give me all of the files contained in files and directories, all of my children of my Java IO file. But instead, and then it would have been up to the program itself, the caller of that method, to do all of the filtering. But instead, it encapsulates all of that behavior in an accept method, which then gives you a lot more flexibility, sort of plug and play different filters, different criteria into your application. So I guess the whole idea here is that there's a nice clean separation between the responsibilities of the file class and then the actual filtering criteria which are implemented in your interface. And you've probably seen the word delegation. We'll be talking more about it in later screencasts. So we say that the file class delegates some of its work to the accept method of the filter. Okay, so that's the file. And a lot of the I/O that you'll be doing will be file based. But files aren't the only kind of I/O you can do, right? You can read from databases, you can read over sockets, network connections, and in order to provide nice abstractions over doing I/O, the JDK has two class hierarchies, two sets of APIs called streams. There is an output stream and an input stream. An output stream is for sending byte-based data to some destination, and an input stream is for fetching byte-based data from some source. And as you can see in these class hierarchies here, there are various kinds of output streams. And I'll be looking at some of these in the following slides. So output stream is the base class in that hierarchy. It's abstract, and basically all it knows how to do is to write bytes to some destination. So it has methods like write, which will write bytes to the stream. It's overloaded to take a couple of combinations of bytes. And then you can close an output stream, and then you can flush an output stream, basically send any pending output to the underlying stream. Some examples of output streams: there's something called a byte array output stream, which will write to a byte array in memory, so it's sort of an in-memory buffer. Piped output stream is paired with a piped input stream to send data between threads in a thread-safe and concurrent manner. And then object output stream is used for writing objects to a stream using something called Java serialization that we might discuss in a later screencast. A file output stream writes bytes to a file. So notice that all file output stream knows how to do is implement that output stream contract, that output stream interface, if you will, and it takes bytes and writes it to a file. It can't write anything else. It can't write strings. It can't write ints. We'll see that there are other classes for that. The file output stream has a constructor that either takes a file object, or the file's name, and it can throw a file not found exception if that file, well, doesn't exist. There's another kind of output stream called filter output stream, and the whole idea is that it's built around another kind of output stream, such as a file output stream or a byte array output stream, and performs some processing on the bytes before ultimately delegating it off to, or ultimately sending the bytes off to the underlying output stream. So, for instance, there is a class called buffered output stream, which implements the write method, but will buffer the data up into chunks before writing it off to some other output stream. So you can imagine, if you wanted to have an in-memory cache of data that buffers up before written to a file, you could use buffered output stream for that. Data output stream is an important class. What it does is it provides methods for writing Java's primitive types in a machine-independent format. So data output stream has methods that will write a long or write a car out to underlying output stream. And then print stream, which writes data in a human readable format and doesn't throw exceptions. And print stream may be familiar to you because it's the type of system.out and system.error. They're both print streams. So what print stream provides is methods like print and printline that, here again, write out strings that are human readable and do it without throwing exceptions. It just makes it a little easier to use. Now, even though it doesn't have exception, that the print and printline methods don't throw exceptions, doesn't mean that you can't determine when something goes wrong. If you're working a lot with print streams, then you should be invoking the hasError method to determine whether or not an error has occurred. Okay, so here's an example of using output streams. It simply writes it writes some double values to a file. So it's going to read the values as text from the command line, convert them into doubles, and then write them out to a file. So how do we do this? Okay, well, the first thing we need to do is to get a file to write to. And that's what the beginning of this main method does. It creates a new file output stream with and the name of the file is specified in the first command line argument. Now, the constructor for file output stream, if you look at its API docs, it will say that it might throw a file not found exception. And so, because file not found exception is a checked exception, the compiler, the language, forces us to either wrap the call to new file output stream in a try-catch block, or we could have added the a throws file not found exception to the declaration of the main method. Because it's the main method and we don't really want the entire exception and stack trace to escape our program, we catch the file not found exception and print out an error message. And notice, for the sake of demonstration, we've used an error field, a static error field, to refer to system.error. This basically just shows that system.error is a print stream and reminds you that it does have a printline method. But if we've gotten this far, it means that we've successfully created our file output stream. Now, file output stream only knows how to write bytes to a file, but we don't want to write bytes to a file. We want to write doubles to a file. And the way we do that is that we wrap a data output stream that has a method like write double. We wrap a data output stream around our file output stream, and we're going to work with that. So we create one of these new data output streams. We'll iterate through the rest of our command line arguments. And for each one of those command line arguments, we will convert that string into a double using double.parseDouble. And then we'll write the value of that double to our data output stream. Writing the double to a data output stream will convert that double into bytes that represent the double, and then write it to the underlying output stream, which in this case is a file output stream. There are a couple of things that could go wrong. while running this code. If the string on the command line is not a valid double, you'll get a number format exception. We'll print an error accordingly. Or if some other IO exception, if an IO exception occurs while writing the double to the data output stream and ultimately to the file, if an IO exception occurs there, we will print that out and we'll exit the VM. And so now if I run that program, so if I say Java class path target/classes, this is where Maven puts the classes, edu pdx cs410j package core write doubles, and I give it some double values, like I'll write to a file. We'll call it doubles.out 1.2.3.2 4.56. Always helps to have the name of the class spelled right. Write doubles. Now if we try to look at double.out, we'll see that it's binary. Not surprising, because we wrote out a bunch of doubles that could convert to bytes. Well, so why is this interesting? Well, again, these output streams that we've been working with are good examples of behavior delegation and separation of responsibilities. So in that last example, what I wanted to do was I wanted to write some doubles to a file. And instead of there being one class that provided all of that functionality, we leveraged a couple of classes to do it. So let's start from the bottom here and go up. First of all, we wanted to write to a file, so we used a Java IO file. But we wanted to write to a file, so we used a FileOutputStream, which provided the some underlying implementation of writing to a file. But we didn't want to write just bytes to that file. We wanted to write a double, and so for that we used a data output stream. So when I call write double, that write double method on data output stream converts the double to bytes, writes it to an underlying file output stream, which then writes it to an underlying file. Another way to look at this is as object composition, or the object onion. In the middle of the onion, you've got a file, and wrapped around that you have a file output stream, and wrapped around that you have a data output stream. And so by separating out these responsibilities, you really have a very flexible toolbox of parts that you can then combine together to solve your problem, as opposed to having one big monolithic solution that needs to accommodate all sorts of different permutations and combinations. We'll see lots of other examples in this course of how by separating out responsibilities among different objects or different parts of your code, you can make things much more focused, much more testable, and ultimately much more flexible. Okay, now that we've seen how output streams are used to write bytes to some destination, let's look at the other side, the input streams. They're basically the mirror image of each other, where an output stream has a write method, an input stream will have a read method. So here again, at the top of the class hierarchy, there is this class called inputStream that is responsible for reading bytes. And it has methods like available, returns the number of available bytes that can be read without blocking. You can close input streams, and then you can read bytes into a byte array, and then you can skip over some number of bytes in your stream. The examples of the input stream mirror the examples of the output stream. So there's a byte array input stream for reading bytes from a byte array in memory. The pipe input stream goes to the piped output stream. And there's also a class called sequence input stream, which is used for reading multiple input streams in some order. So let's say that you've got a very large piece of data that's spread over multiple files. You can read all of those. So you can create a sequence input stream over all of those files that would make it look like it was just one big continuous input stream. So the analog to file output stream is file input stream, and it's used for reading bytes from a file. And again, it's constructed from a file object or from the name of a file. It may throw a file not found exception if it doesn't exist. A filtered input stream provides the same kind of filtering around input streams that the filter output stream did around output streams. So it does some processing on the bytes that are read. So here again, you've got a buffered input stream. You've got a data input stream, which is used to read Java's primitive types. And there are things like a pushback input stream that allows you to read a little bit from a stream and then push it back in there if you don't want to consume it right away. And those of you who have taken your compilers class have studied look-ahead parsers and all that kind of stuff, and you can imagine how that might be implemented using a pushback input stream. So here's an example of using input streams to read doubles from a file. It looks a lot like the write doubles program. The first thing that we're going to do is create a file from the first command line argument by creating a file input stream. And here again, if the file doesn't exist, it'll throw a file not found exception. Once I have my file input stream, I'm going to wrap a data input stream around that. And then, until something blows up, I'm going to keep reading doubles from that input stream, and I'm going to print it out. And note, just for the sake of example, I'm going to flush the output to my print stream, which in this case is system.out. Now, when I'm done reading doubles from my file, I'm going to catch the end of file exception that's thrown, and I'm going to break out of my my while loop. If something else goes wrong, though, some other kind of I/O exception, like it can't read the file or the file is corrupted, meaning that it doesn't contain the right number of bytes, it'll get an I/O exception. I'm going to print that out, and I'm going to exit the VM with an error. So now when we run this program, we want read doubles. Actually, first let's see the let's see what happens when it has a non-existent file. No such file does not exist. Ooh, and it gets a null pointer exception. You know what? And why is that? Because I print out the error, but then I never, system.exit, I never return from the main method. Well, there's a bug. Live coding at its finest here at Advanced Java at Portland State University. Anyway, instead of reading from a file that doesn't exist, we'll read from an existing file, like double.out. And there it prints out the files that we had written before, 1.23, 2.34, and 4.56. Actually, let's just take a look at the size of double.out, and sure enough, it's 24 bytes long because each double is 8 bytes. So here again, we've seen how you create this object onion to do your work, and you leverage these parts that all perform a single responsibility, that all have limited behavior. And you can combine them in such a way that you can ultimately fulfill your task. A couple of things about this code, which is kind of yucky. There's no nice way of telling the data input stream or asking it whether or not it's done. Instead, you have to catch that in a file exception, which is kind of unpleasant. Not the end of the world, but it's kind of an unusual programming pattern. And note that just for the sake of argument, that I used the print method here, and then I flushed after every call to print, and then I did a print line here at the end. Alternatively, I suppose I could have written all of these to a string builder or something, and then printed out the toString of that. So the streams were in the Java I/O API from the very beginning, and they worked great for byte data, but working with text was a little awkward, especially when you had it handed ASCII okay, but really more international character sets, all of Unicode. There were just some things missing from the Stream API. Instead of trying to augment the Stream API to also handle text, they introduced a couple of hierarchies that are optimized and designed for working with text. So instead of output stream, you have something called a writer, which is responsible for writing text to some destination, and a reader that's for reading text. And the writers and the readers work a lot like the input and the output streams, in that there are various subclasses that have specific responsibilities, and that they can be combined to then do higher level things. So here again, sort of the inventory of what these classes do. Writer has methods like write, which will write some characters or strings to some destination. Close will close a writer, and then also flush will send all the pending text to the destination. Some examples of writers: there's a buffered writer that buffers up text, a character array, a char array writer, which writes text to a character array in memory, filter writers that do filtering, piped writers for multi-threaded concurrent programs, and then output stream writer. And what output stream writer does is it provides a bridge between the writer interface, the writer hierarchy, and the output stream hierarchy. And so, let's say that I want to write to a network socket. A network socket only knows how to deal with bytes, and so I'm going to have an output stream for that. But what I want to do is I want to write characters. I don't want to write just pure bytes to that network socket output stream. So I'm going to use this output stream writer as sort of an adapter of sorts. That output stream writer, has a write method that takes a character array, but then will convert that character array into a byte array and send it to that underlying output stream. Print writer is a lot like print stream in that it prints formatted text, pretty text, off to some other writer. So it'll take a string, for instance, where a writer just takes a character array. And it has the print and print line methods, but I guess one difference is that it's not automatically flushed. And the stream, the underlying stream, is not automatically flushed. String writer writes to a string in memory, and ultimately it's a string builder underneath the covers, and you can get access to that by calling get buffer. And there's also toString, which will convert that string writer, so the data has been written to the string writer, to a string and return that. And there's also a file writer, which writes text to a file. So here is an example of writing some text to a file, very similar to writing those doubles. I guess we're going to show an example here of wrapping a print writer around system.error. You might want to make sure that you use true here to automatically flush the stream after some data has been written to it. First thing we're going to do is we're going to create a new file writer from that first command line argument, and I'm just going to take every other command line argument and write it to that file writer. When all done, I'm going to do a flush and a close. If there are any problems, including if the file does not exist, an IO exception will occur, and we'll just print it out. I got a little lazy here on the exception handling. You've already seen examples of it. You can probably guess what you really need to do in the real world. So, running this program, to file, and I'll name the file text.out, and this screencast is long. Now if we look at that file, yep, there's its contents. Again, the important lesson that I want you to take away here is that we've used different objects that have different responsibilities in a way that they can be combined and wrapped to one another, wrapped around one another. Notice that we had a print stream, we wrapped a print writer around that. This abstraction really it does a couple of things. It keeps responsibilities separate, but it also simplifies your program by hiding what's really going on, right? There's because any given line of code is dealing with the with the objects sort of in the abstract. So, like for instance, here our writer, it's not a file writer. It's just some writer, because the only method that we rely on there is just a write method. We don't care that it's writing to a file. So, like this code right here, this for loop, doesn't care that it's writing to a file. It just knows that it's writing to some writer out there. And this is really important. This is sort of the essence behind that program to the interface that I keep talking about. That you want your code to deal with sort of the most abstract possible, because it allows you then to reuse that same code with a different implementation of that abstraction. So let's say instead of writing to a file, you wanted to write to a database or to a socket or something like that. You just have to change which writer it's referring to. The code that actually works with that writer, it doesn't care. Okay, on the other side of the I/O fence is Java I/O Reader. Well, which reads characters from some source. Yes, it has a read method. It also has a method called ready, which determines whether or not a reader has more text to read. This is actually really convenient because we'll see that when you loop, we just keep asking the reader, "Hey, are you ready yet? Are you ready yet?" And it'll tell you whether or not you should go ahead and try to read from it. You can close a reader, and you can skip some number of characters. Examples of readers: you got character array reader. They're basically the analogs to all the writers. Filter reader, piped reader, string reader, input stream reader. Here again, for reading one of those byte-based input streams, reading text from it. And then the buffered reader is a filter reader that will buffer text as it reads, and this is the class that has the read line method. So if you guys think back to your CS 101, probably one of the first classes that you wrote, read input from read from standard input one line at a time. And so the way to get the read line functionality is to use the buffered reader class in Java. And here we'll see an example of that. So we want to read from standard input. So standard input is system.in, but if you look at the type of that field, it is an input stream. So it reads bytes from standard in. We don't want to read bytes. We want to read text. We want to read characters. So okay, we basically need to use an adapter that will give us that reader functionality on top of an input stream. And the way we do that is we wrap our system.in, we wrap a input stream reader around that guy, and now we've got an implementation of the reader interface or reader behavior that we can then work with. Now, we don't want to read just text. We want to read a line of text from that. So then we wrap a buffered reader around that input stream reader. Here again, we're putting together our object onion. In the middle of the onion is that input stream for system.in. We wrap an input stream reader around that, and then we wrap a buffered reader around that. And now, when we call readLine on that buffered reader, it'll read a line of text from that input stream reader, which will then read a bunch of bytes from system.in, find the new line character, and return just that one line. Note also, for the sake of demonstration, we are using a string writer to build up the text that we're writing. So we're going to sit here and read from our buffered reader just until it reaches the end. Or sorry, until you type -1. So we'll read each line from our buffered reader. If that line is -1, well, we're done with our loop. We'll exit out. Otherwise, we will print that line, write that line to our string writer. If anything goes wrong and an IO exception occurs, we'll print it out and exit. Otherwise, we've gotten down here to the end. We'll simply print out the toString value of the string writer, that text variable, to standard out. And running this program. Okay. Hello, internet. Whatever. -1, we're done. So I've typed all that stuff. Every time I've typed it into standard input, and every time I hit return, then the call to read line returns. It buffers it up into that string writer, and when I hit -1, it detects the end and prints out what's there already in the string buffer, which is hello internet. Okay, well, I think that's enough for now. And so that's the Java's facilities for performing I/O. We first saw a discussion of the Java I/O file object, which sort of gives you access to files on a file system, but it abstracts things in a way that your code can be platform independent, even though ultimately it's running on top of an operating system like Windows or Unix that has its own representations of files and how you work with them. Then we discussed how to do byte-based I/O using input streams and output streams. We saw some good object-oriented techniques, such as behavior delegation, separation of responsibilities, and here again that object onion where you're wrapping objects inside other objects. And then finally we saw how to do text I/O with the readers and writers. I think that's enough for right now. As always, thank you for watching the Advanced Java Programming screencast at Portland State University.